All right. Hello everyone. I'm going to tell you today a bit about how we do recommendations, or a bit portion of how we do recommendations. Well, unfortunately, I don't know how you see my presentation and myself. I hope it's all right. Okay. So let's get started. So first, the motivation why we do what we want to do and why we want to do it. Okay. Like first, what is Criteo? Criteo is built around the personalized advertising. So we know something about user, and we want to show some ads to it that will help our clients. The quirk is we have about 3 billion users and about 1 billion products that we need to know something about to recommend them efficiently. So we often want to know which products are more similar to each other. So the problem is more general than a recommendation. We want some kind of similarity between products that we can use. Then we can leverage the information about products that users seen, and then try to tell which users have more similar history. And then at the end, like which products for example, from eBay can we recommend to those that have their own history, that have never visited eBay before, sort of the user acquisition type. So one of the standard approaches in the industry is to, okay, we have the data as user timelines. Let's treat them as sequences and basically treat them as implicit feedback. We can try to do, based on that, our recommendations or extract kind of similarity between items in a worth of X style. And we can factorize the matrix, or we can directly learn a latent factor model over that. So there are obviously a plethora of methods to do that. More scalable, less scalable, with powerful models. And there are a bunch of them, of course. But one of the main problems and differences of Criteo with what exists in the literature is that our data set is huge compared to what it's used. And there are some approaches to do really billion scale recommendations and similarities, but they really require a non-trivial amount of engineering. Basically, they cannot be expressed in a MapReduce architecture efficiently. And we were looking for something that both could be expressed in a MapReduce architecture or similar one like Spark, and it was doing well enough. So, of course, there are multiple areas of improvement and research in this area to learn for a better target, not to predict like implicit feedback, but to try to directly optimize for a business goal. Another approach is let's have better models. But the problem that we actually faced was mostly scalability and the quirks of our data. And I'm going to tell it today about a bit. So we found the most scalable and still the very performant approach in terms of similarities and recommendations. It's PMI SVD that I'm going to talk about. So the approach is very simple. So you compute the product-to-product co-counts and put them in the matrix. Basically, it can be seen as the product of user item matrix with itself. Then we transform it into some form of similarity, right? You can imagine that it could be a TF-IDF or some other form of similarity. But the one that we found works the best is PMI, pointwise mutual information. We extract top singular vectors of this matrix out of product by product matrix with the PMI measurements in between. And we can use linear combination of those. You can think of it as a embeddings of products, as a user embedding. And then basically this is just a simple comparison of our method. So it performs way better than just a simple SVD and on par with a weighted ALS. The thing is, it is way more scalable and can go up to billions of products without a lot of hardware and a huge cluster. So of course, this idea is not new, right? It's been used a lot, of course, using SVD, non-SGD based, but real SVD for recommendations is not new. Generalizing it with some similarity functions has been also been written about, and the PMI, of course, has been extensively used by LSA and NLP communities as well. So how do we actually scale the SVD, right? Like, what are existing approaches, and are they enough? Can we go to 1 billion products? Actually, no, we could not. So there are a bunch of methods. The first one that usually comes to mind for recommendation and information retrieval communities is SGD based, like Giraffe. The problem, so it's great, like it's fully distributed in the sense that you don't have to use a lot of memory on any single node. But the thing is, the network communication for this kind of frameworks still has to scale quadratically with the number of products that you have, and that actually is very, very expensive. So you need a large cluster to actually do some reasonable job. So we thought we could do better than that. There are partially distributed SVDs like SparkML SVD available there. The problem there, it's only partially distributed. So it distributes really well the multiplication by the sparse matrix, but unfortunately it has to store all the latent factors that you're learning at the master node, which becomes very quickly not feasible, and also very slow because you do this simplified SVD on the master node. So for example, for 1 billion products and 100 latent factors, you would require on the order of a terabyte of RAM on your master node, and it will be slow as well. There exist some approaches that will allow you fully distributed SVD. So basically, you distribute both your sparse matrix multiplication, and you don't need to do SVD on this on the latent factors. It's been implemented in Dask, but the approach is solid. But this implementation did not suit us because it was not scaling further than 30 million products. So we needed to go to 1 billion. So I'm going to tell you how we did it and what our approach is based on. So first of all, imagine we have a real SVD notated as a USV transpose here, and we have some given to us tall and skinny projection that when you project A onto it and then back, you retain most of the information contained in A. And the Q really has to be tall and skinny, meaning that it has to have very few rows. That is going to work. If we have such a projection, then we can decompose Q and A part of Q transpose A into U hat SV transpose, and we can immediately see by uniqueness of SVD decomposition, by uniqueness of our left singular vectors, that our tall and skinny projection times U hat, which is a K by K matrix, gives us original U. And finding U hat is relatively cheap, because if we take the part Q transpose A and transpose it, we get a tall and skinny matrix, meaning that it has not that many columns. So we do QR decomposition, which we can do in MapReduce architectures very efficiently. And we take the R part of it, which is K by K matrix. So it's very, very small. It's just in the order of how many latent factors you need. And you do SVD over that. You obtain your U hat, and then you can do, you can go to the original U. You can fully decompose it. So the algorithm looks like this. You generate a random matrix, tall and skinny matrix, G, with the elements drawn from Gaussian distribution. You do a couple of iterations of power iteration just to improve your Q, and you do QR and basically orthogonalize all the columns there. Then you do QR decomposition of this projection multiplied by A. You find your R, you do SVD over it, and then you can compute your final U, so all the left singular vectors that you were looking for. And this is effectively, they're embedded in all your products. And the thing is, this kind of algorithms are very good in a provable way. So basically, there are very sharp bounds published in 2013 that even if you have a square matrix like in order of billions, and you look for 100 latent factors, with a small oversampling, meaning that you need to take 130 latent factors and just 3 matrix multiplications, you can get an error within 4 or 5 singular values, k+1 singular values, which means that it's effectively as good as SVD if you take a slightly larger number of latent factors. So I'll walk you through a bit through the implementation, some implementation details. Okay, so in our SVD, like in general, you just need to implement 4 distributed operations. First one is super easy. You just generate a random matrix G. So you can do that distributed way. It's embarrassingly parallel, so it's very easy. Then you need to be able to multiply a dense distributed matrix B by a single block, which is also easy. You just send it over to all the nodes and you multiply it locally, no problem. And then there are a bit tricky parts. QR decomposition of tall and skinny matrix B and the multiplication of sparse A by a dense matrix B. So like our distributed block matrix is a standard approach in Spark. So you split your array into block matrices, square and non-square, doesn't really matter, and then you unite them into partitions of these block matrices. So how do we do tall and skinny QR decomposition? It's been published again in 2013, called implicit QR factorization. So what you do is you split your tall and skinny B in multiple partitions, and in every partition you do QR decomposition on the submatrix that you got. You get your R, which are k by k at this moment, and you send them further to the next level. And you do sort of a tree reduce thing where you make sure that at every level, at every node, you have only a couple of k by k matrices R, and basically you're not limited by memory. And this works really, really well. And then at the end, you get your R out of the QR decomposition. And it can be shown that this is unique and a real R that you would get in the non-distributed QR decomposition. The problem is we want to get Q, right? We want to get orthonormalized matrices, orthonormalized columns. So how do we get that? We just take our original B and we multiply by the inverse of R. And if your original B was well initialized from the Gaussian distribution, and your rank of your matrix A is way larger than K, then you're good to go. You can invert. There won't be any problem there. So if we want to multiply a square sparse matrix A by tall and skinny matrix, dense matrix B, then basically it can be done in multiple ways in Spark. But the main problem there will be that you have little control over where you send your data exactly. So with a bit of tricks, one of the best way to do it that we could find is basically we split A into multiple RDDs. Over a bunch of rows, and then we partition it by column, and basically we have our blocks of B locally within the same nodes that partitions of A are stored. So basically almost no shuffle required, only on the reduce stage when you sum them together. And there is a very small overhead of splitting A into multiple RDDs. So the properties of our solution are actually very nice. So it's probably a really well approximation of SVD. It can be very easily be expressed in MapReduce and Spark API. The memory requirements on every node are completely independent of your initial matrix size, so it's fully distributed in the true sense. And we get the deterministic results, which is also very nice from engineering perspective, because you can have no regression tests and other stuff that makes it very nice. And of course, it's motivated by a range of works and the randomized algorithms and the MapReduce algorithms. So we open sourced our RSVD implementation, which is the most scalable distributed SVD implementation in open source that I'm aware of. So the second part of my talk will be a bit about what kind of quirks we have in our data and how we deal with them. So you remember that we were talking about user timelines, and let's look at them as walks on a graph. So products are vertices in our graph, and the user starts somewhere in this graph on a single vertex, and then it transfers to another product, so like viewing pattern, for example, within the same partner, like eBay, or going further to another partners, right? So it's the graph that captures all the products available to user on the web. Yep. And then you can see that this walk is guided by, you can understand that it's guided by some form of attractors that will make a bit more precise a bit later. So for example, if you started browsing one product on eBay, it is very likely that the next product that you will see in your timeline will be from eBay. If you started browsing some jeans, it will be very likely that you will look at another pair of jeans. And there are other patterns like product complementarity and other stuff. So this walk is very, very guided. But sometimes, and we can see from this walker perspective, then in this graph, this sort of attractors are communities. So the sort of portions of the graph where the random walker gets stuck for a longer period of time. But the thing is, not all of them are very useful. Actually, if you want to, depending on the task that you're trying to do, right? For example, you want to compute the best product for the user, independent of what was the partner, like a website like eBay, that the user started with. So in this sense, this sort of communities of partners, they make no sense. They're useless to us. So we want maybe to remove them. If we want to compute the best product, for example, the user viewed jeans, and we want to compute the best matching product from another category, then the communities inside categories does not make much sense. It won't contain any useful information to us. And the list goes on. So the thing is, the scale is so large, so we cannot really do the supervised learning, which would be great, right? You would just learn your embeddings for the task. But you cannot really do that easily with the 1 billion products. So is there a way to remove this redundant community information without direct supervision on the task that we're learning, but still without losing much information, the rest information about the structure of the graph? Because of course you can imagine you can remove all the edges, for example, and then of course all the communities are lost, but you don't recover any useful information to yourself. So you sort of want to remove what you know and keep what you don't know. So there is an approach to that, which we call community debiasing approach, and it's based on the known results from the study of sparse blended partition graphs. And by sparse, I mean that the number of the probability of having an edge inside community is growing linearly with the size of the graph. So it has only basically some constant number of degrees inside the community and outside of the community as well. So it's a very sparse graph. And this result states that basically if the degree inside, if the squared difference between inside degree and outside degree between communities is smaller than some value that you can compute, then it's impossible, in information theoretic, from information theoretic perspective, to recover these two communities. And we use this to actually debias the graph that we're dealing with. So in a simple case, we have a graph that is contains two communities, like two partners, for example. Then we can subtract the then submatrices A and B contain the edges that go inside inside these communities, like edges connecting products from the same partner, from eBay and Verbaudet, for example. And AB and BA are the submatrices containing information between the edges, or about the edges between two communities. And if we subtract some constant multiple of A on the diagonal and the constant multiple of B on the diagonal from this matrix, we can, with the specifically, if we find specific parameters alpha A and alpha B, then we can probably remove all the community structure from the graph about these two communities. So now the question is, how does it impact the spectrum of our like adjacency matrix in this sense? How does it change the eigenvalues, basically singular values of our matrix? So by some sensitivity analysis, we can see that if we have our initial P and we add to it P dot, then basically the changes in singular values of all the singular vectors will be proportional to their dot product with the community structure in the graph. So basically, the more sort of this singular values commute with the graph structure, the more their singular values will be depressed. So what it means is that with this approach, if we subtract this submatrices from the original matrix and we do the SVD decomposition, it means that top singular values and top singular vectors will be uncorrelated with the community structure. That's sort of what we wanted. Of course, the effect is not as simple as that, because we'll change actually the eigenvectors of the original matrix. But this sort of gets a sense of what we're doing there. So if we have multiple communities, we can actually generalize this method to multiple communities. Then we iteratively consider two communities things. So we take one community and everything and the rest we treat as another community. And then we go on with the second community and the rest, and then the third and the rest. And basically we can form a system of linear equations with the parameters alpha to be learned. And then we can sort of minimize these differences between degrees, and in a probable way sort of remove the most information about the partners while retaining the other structure information in the graph. So to give you a concrete example of how it could work. So we started with original graph that was very partner biased. Well, because it's normal, right? The users browse within partners, which is fine. But we wanted to have some kind of similarity within categories. So we want to see jeans on eBay be matched to jeans on other websites, for example. And then if you do this kind of SVD on the graph and you find the top single values and you try to do classification based on them, the the category classification error will be very, very large. And for partners, we recover all of them. So if we debias some of the top ones, we immediately lose a lot of information about the partners and recover way more information about the categories, right? That's what we expect, because we depress the singular vectors, we move them to the end of the spectrum that are commuting with the community structure, and sort of the other information flows up in our truncated SVD. And if we debias all of them, like, we lose even more partner information, we get even more category information. That's one of the approaches how we treat data. Okay, so thank you. Again, we open sourced our SVD implementation. You can clone, fork, send PRs, and if you have any questions, there is some time left. Yep, I can.